In this video, we will be looking at section 4.1, which covers exponential functions. So we're going to start with a definition of an exponential growth or an exponential decay function. So an exponential growth or decay function is a function that grows or shrinks at a constant percent growth rate. So you'll notice this is different than a linear function because it grows by a set amount. This is growing by a constant percent or shrinking. Exponential functions can be thought of as f of x equals a times 1 plus r to the x power, or f of x equals ab to the x power, where b is equal to 1 plus r. You may think, why would we write it two different ways? But sometimes it's easier to work with this one, sometimes it's easier to work with this one. In this form of the function, a is our initial or starting value of the function, so it's where we begin. R is our percent growth rate or percent decay rate, and we're going to write that percent as a decimal. B, this B here, is our growth factor or growth multiplier, and we are going to restrict B to only be positive values. We're not going to deal with anything negative. So we're going to start with some exponential models. A population is currently 6,000 and has been increasing by 1.2% each day. Write an exponential model for the population and estimate the population in 2 weeks. So I kind of like to think of this as f of x is equal to a times 1 plus r raised to the x power because we were given our percent increase. So in this case, we'll have f of x is equal to a, that's our starting value. In this case, that's 6,000, times 1 plus our growth rate. Our growth rate is 1.2%, and that as a decimal is 0.012. So we'll have 1 plus 0.012, that's raised to the x power. But I can add 1 plus 0.012. That'll give us f of x is equal to 6,000 times 1.012 to the x power. That is a function that represents the population. Now it wants us to estimate the population in 2 weeks. Be careful though, this percent change is each day. So if we're looking for 2 weeks, we are going to let x be equal to 14 because there's 14 days in 2 weeks. So if we evaluate our function f at 14, that's going to be our 6,000 times 1.012 raised to the 14th power. That's showing up really dark. Let's see if we can turn on a light. A little bit better. So 6,000 times 1.012 to the 14th. That's about 7,090.5255. Because we're talking about population and a number of people, let's take that to 7,091. So there will be approximately 7,091 people in 2 weeks. Next up, a business purchases $125,000 of office furniture, which depreciates at a constant rate of 12% each year. Write an exponential model for the value of the furniture and find the residual value of the furniture 6 years after purchase. So we have our initial value, but we have to understand what these other words mean. So it depreciates, that means it's going to be worth less in the future. The amount of money it's worth is going down. It's depreciating at a rate of 12%. And then we want to find the residual value, meaning how much is it worth at the end of 6 years. So let's start with our function. We'll have f of x equals, we are starting at 125,000 times 1, but we're not adding a percentage. We are losing 12%. So we're going to subtract 0.12, and that's raised to the x power. So our function this time will be f of x equals 125,000 times 1 minus 0.12 is 0.88, and that is raised to the x power. The value of the furniture is depreciating at 12% per year. So x is measured in years, and we want to find the residual value after 6 years. So we will plug in x equals 6. So we want to evaluate our function at x equals 6. That'll be 125,000 times 0.88 raised to the, and we were plugging in x equals 6. We are getting 58,050.51. We're measuring in money, so I'll round to the nearest penny. So $58,050.51 is how much that furniture is going to be worth. Next up, we're going to see if we can find equations of exponential functions. So first up, we want to find a formula for an exponential function passing through the points -3, 4 and 3, 2. Now remember, we had two different formulas we could use for exponential functions. They were either f of x is equal to a times 1 plus r to the x, or f of x equals ab to the x. Now I think that ab to the x might look a little bit easier to work with, so we're going to try using this form this time. It says find a formula for an exponential function passing through the points -3, 4 and 3, 2. Well, I know I can plug those into the equation at least. So let's start with -3, 4. If I plug that into what I have, -3 is my x, 4 is my y, which is f of x. So that'll give me 4 is equal to ab to the -3. If I plug in the other point, I will have 2 is equal to ab to the +3. But we're trying to find the exponential function, so I need to find both a and b. If I think back to how I solve two equations at once in linear equations, I can either graph, but I'm not thinking I'm going to be graphing these anytime soon. I could use substitution or elimination. I'm not exactly sure how elimination would work in this case, but the idea behind substitution might work. For substitution, we have to get a variable by itself. So I either need to take 4 equals ab to the -3 and get a variable by itself, or 2 equals ab to the 3 and get a variable by itself. I think it's going to be easier to work with the second one because I can get a by itself by dividing both sides by b cubed. And that tells me a is equal to 2 over b cubed. Now I know what a is, and I can plug that into the other equation. So when I plug that in, I'm going to have 4 is equal to a, which we said is 2 over b cubed, times b to the -3. But we have to remember what a negative exponent means. A negative exponent means move it to the denominator. So I'm looking at 4 equals 2 over b cubed times 1 over b cubed, or 4 is equal to 2 over b to the 6th. Man, I'm still trying to solve for b here. So I'll multiply both sides by b to the 6th, and I will have 4b to the 6th is equal to 2. I can divide both sides by 4. I get b to the 6th is equal to 2/4, which is 1/2. And to get the b completely by itself, I'm going to raise both sides to the 1/6 power. Now the reason behind that is if I raise b to the 6th to the 1/6 power, that's the case where I multiply exponents. 6 times 1/6 is 1, and b to the 1 is equal to b. So I will have b completely by itself if I do this. I'm going to raise both sides to the 1/6 power. It's not pretty, but I have an expression for b. b is equal to 1/2 raised to the 1/6 power. I can figure out what that is on my calculator. Let's see what it looks like. Let's turn that light back on. 1/2 raised to the 1/6 power is about 0.8908987181. That's not very pretty. I'm going to leave it as 1/2 to the 1/6 power, and we'll take it to a decimal later if we need to. Now that I know what b is, I need to find a. Well, we said a is equal to 2 divided by b cubed. So let's work up here just so I have some more space. A is equal to 2 over, we know what b is. B is 1/2 raised to the 1/6 power, and that's cubed from our equation about a. This is a case where I multiply exponents, so a is equal to 2 over 1/2 raised to the 1/6 times 3, so that'd be 3/6, which is 1/2. And boy, that is not pretty either. Let's see what that looks like. We have 2 divided by 1/2 raised to the 1/2 power. 2.82 stuff. Alright, I don't generally like using decimals, but I think it's time. So our a value is about equal to, let's take these out to 4 decimal places. So 2.8284. And our b value was 1/2 to the 1/6 power, which we had up here already, and that's approximately equal to 0.8909. So now that we have an a and a b value, we can write our equation. We were using f of x equals ab to the x. I'm going to write it up here just because that's where I have room. We'll have f of x is equal to, our a value was 2.8284 times our b value, which was 0.8909 raised to the x power. That's what I'm looking for. I know it's not pretty, but it is what I'm looking for. Let's try the second one. I have some sort of feeling in my brain that the second one isn't going to be as bad. We want to find a formula for the exponential function passing through the points 0, 9,000, and 372. So let's set up our equations. If I'm plugging into f of x equals ab to the x, then I will have 9,000 equals ab to the 0 power. Wait, hold up. B to the 0 power. Anything to the 0 power is 1. So this is 9,000 equals a times 1, but a times 1 is just a. A is 9,000. I'm halfway there. Now that I know what a is, I just have to find b. So let's use this other point. That'll give us 72 is equal to a, we already know, is 9,000, times b raised to the 3rd power. I need to solve for b, so I'll start by dividing both sides by 9,000. Wonder if that's a nice fraction. Be a surprise in these problems. We want to take 72 divided by 9,000 if I hit math, enter, enter, that tells me that's 1 over 125. So I get 1 over 125 is equal to b cubed. So to get b by itself, I'm going to raise both sides to the 1/3 power. And the great thing about this calculator is I can say raise it, and it's going to take what I wrote last, and I want to raise it to the 1/3 power, and I get b equals 0.2. I now have a and b, so I can write my formula. We'll have f of x is equal to my a value, 9,000, times my b value, 0.2, raised to the x. A little bit nicer this time around. Glad we didn't have to go through all those steps again. But hey, it's good practice. Next up, an investment was valued at $11,000 in the year 1995. The value appreciated means it went up to $14,000 by the year 2008. What was the annual growth rate between 1995 and 2008? We are going to assume that the value continues to grow by the same percentage. And then we want to know what is the investment's value in the year 2012. Just to make things a little bit easier, when I'm working on this problem, I'm going to let x be the number of years since 1995. Because if I do that, then I can say that when x equals 0, so in the year 1995, the value was 11,000. In the year 2008, well, we have to figure out how many years after 1995 is 2008. Well, 2008 minus 1995, that's 13. And after 13 years, it is now equal to 14,000. So now I can do what I did in the last problem and find an equation. Using this point here, I'm going to find that my a value is 11,000 because my a value is my starting value. So now I need to find b. So I'm going to use this point here. We'll have 14,000 is equal to my a value, 11,000 times b to the 13th power. If I divide both sides by 11,000, I will get 14/11 is equal to b to the 13th power. And if I raise both sides to the 1/13, I get b is about equal to, because there's no way this one's going to be nice. We want to take 14 divided by 11 and raise it to the 1/13 power. It looks like b is about equal to 1.0187. The question asked us for the percentage growth rate that we experienced. This is the growth multiplier. Remember that b is equal to 1 plus r. So if I want to find the actual rate itself, I need to subtract 1 from this. That'll be about 0.0187, which as a percentage is 1.87%. Finally, it wants us to find the investment's value in the year 2012. Well, I have an equation that's y equals our a value, 11,000, times my b value, which was about 1.0187, raised to the x. X is the number of years since 1995, so I need to figure out how many years after 1995 is 2012, and that's 17. So I need to plug in 17. And we'll get our value is 11,000 times 1.0187 raised to the 17th power, and I'm getting about $15,072.31. All right, next up is the very classic exponential problem involving compound interest. And to use compound interest, we need the compound interest formula, which says a of t is equal to a times 1 plus r over k raised to the kt power. I've seen this formula written in other forms. You may have seen it as a equals p times 1 plus r over n raised to the nt power. It's the same formula, it's just using different variables. So given the equation in this form with our r's, k's, t's, and a's, a of t is the account value, so that's how much the whole thing is worth. T is time, and it's measured in years. Our lowercase a is the starting amount in the account, often called the principal. R is our annual percentage rate, also known as APR, and that's measured, that's also called the nominal rate. K counts the number of times we are compounding in 1 year. So if we are compounding annually, that means once per year, so K is 1. If we're compounding semi-annually, then K equals 2 because that's twice a year. Quarterly, K equals 4 because that's 4 times per year. Monthly, K equals 12 because monthly is 12 times a year. And daily, we'll go with 365. So let's see if we can use that formula. It says if $6,000 is invested in a bank account at an interest rate of 9% per year, find the amount in the bank after 5 years if interest is compounded annually, semi-annually, quarterly, monthly, and daily. So let's copy over that formula and see if we can plug stuff in. It was a of t is equal to lowercase a times 1 plus r over k raised to the kt power. They're giving us $6,000 in the beginning. That's our lowercase a value. They're telling us that our interest rate is 9% per year. And 9% we write as a decimal as 0.09. We want to find the amount after 5 years. So we'll have t equals 5. And then in each of these cases, we're going to have a different k value. So for annually, k equals 1. For semi-annually, k equals 2. For quarterly, k equals 4. Monthly, k equals 12. And daily, k equals 365. So if I plug into our formula, what we're looking at is a of t is equal to 6,000 times 1 plus 0.09 over whatever k value we're using raised to the k times 5, which I can write as 5k. Now I could go in and type this in my calculator 5 times if I really wanted to and plug in each value of k. But I'm getting more comfortable with my calculator, so I'm going to see if I can use a useful function. If I go to my y equals, I'm going to plug in this function as I see it. 6,000 times 1 plus 0.09 divided by my variable, which I'll use x, raised to the, in parentheses, 5 times x power. Because now I can go to my table, second graph, and that tells me for different values of my variable what I get out. So first up we had k equals 1. I got my value. So when k equals 1, I'm looking at, and you'll notice up here it doesn't show very many decimal places, but down here it does. So if you scroll through you can find it. Since this is money, I'll go out to pennies. We're looking at $9,231.74. Next up we have k equals 2. So I'm going to go down. And that's going to give me $9,317.82. Next up we have k equals 4. So when I go down there I get $9,363.06. Ooh, that doesn't show up well in white. For monthly, I need k equals 12, so I'm going to scroll down until I find 12. And I'm getting a value of $9,394.09. Now I could scroll forever to find 365, or I can go to second window. That'll bring me to my table set. I'm trying to find when x equals 365, so I'm just going to say start at 365. And I'll go back to my table. Then I don't have to scroll the whole way. And it looks like when I have 365, that's $9,409.35. So you may notice that as k gets larger, the value goes up. But it goes up more significantly in the beginning when we go from k equals 1 to k equals 2 or k equals 2 to k equals 3 than it does when we get higher up into monthly and daily. And you might be asking yourself, how far can I go? Can I compound twice a day? 4 times a day? 12 times a day? Every hour? Every minute? Every second? And there is a limit to where this goes. And that leads us to the continuous growth formula. The continuous growth formula looks very similar-ish to the compound interest formula. This says A of t is equal to lowercase a e to the RT power. Just like before, A of t is our account value, how much it's worth. A is our starting value. E, that's the new one. That's going to be Euler's number, and it's about equal to 2.718282. You should have an E button on your calculator, probably in 2 different places. Let's see if we can find it. Just regular lowercase e is on my division symbol. I'd press second division. But there's also this e to the x on my ln button, so I'd use second ln, and that would get me to e as well. We'll see how to use that in just a moment. R is still our continuous growth rate, and t is still time measured in years. So we're going to see if we can use this formula to get a continuous growth rate. So we're going to take that same problem we were working on. If $6,000 is invested in a bank account at an interest rate of 9% per year, find the amount in the bank after 5 years if interest is compounded continuously. So our formula was A of t equals AE to the RT. They told us what we were starting with. We're starting with 6,000. So A is 6,000. They told us our interest rate, R, is 9%, which we write as a decimal as 0.09. And T, they're telling us to use 5 years. So the amount this is worth is 6,000 e raised to the power of 0.09 times 5. So the way I'm going to type this in, we'll zoom out a little bit, is going to be 6,000. Then I'm going to use my second ln to get e raised to the power, and I'm raising it to the power of 0.09 times 5. I'm going to close those parentheses. And I'm getting $9,409.87. This is pretty darn close to what it was when we were compounding daily. It's only like 50 cents more. So the difference between daily and continuously isn't all that great, but there is technically a difference. There's one more thing we're going to look at in this section, and it is the annual percentage yield. And what that gives is the actual percent that a quantity increases in 1 year. And our formula for annual percentage yield is APY, or annual percentage yield, equals 1 plus R over K to the K power minus 1. So let's see if we can use that. Find the annual percentage yield, or APY, for a savings account with an annual percentage rate of 5% compounded monthly. So our formula for APY was 1 plus R over K to the k power minus 1. They're giving us R as 5%, which is 0.05. K, we are compounding monthly, so that's 12 times a year. So our APY is equal to 1 plus 0.05 over 12 raised to the 12th power minus 1. This is one I should be able to just type in my calculator like normal. So that's going to be 1 plus 0.05 divided by 12 raised to the 12th power minus 1. And it looks like that is equal to 0.05116. But it's annual percentage yield, so let's change this into a percent. We move the decimal over 2 places. That's going to be 5.116%. And that will be our annual percentage yield.